In today's assignment, we're going to continue working with the derivative, and the learning outcomes haven't really changed from B5. And if we look at the advice for this section, you'll see all of the advice from B5 still applies. But the big difference between what we did in B5 and B6 is we looked at derivatives at specific locations. So we were coming out with one finite answer, so the slope of the tangent line at a specific spot. But what we're going to do in this section is we're going to sort of shift our thinking, and we're going to start considering the derivative as a function, meaning if I pick a particular value of x, I can find the slope of the tangent line at any location that I want on the graph as long as the graph is differentiable at that point. So we're going to adjust our definition just slightly. In B5, we saw that we were actually plugging in a value a, and everywhere we had an x, we placed that value a. Now we're going to keep it much more general, and we're going to deal with things in terms of x. To determine if something is differentiable or if a function is differentiable, right, we use the definition of the derivative, calculate the expression, and then by looking at the result that we get out, we can determine which values of x the derivative fails. There's going to be three sort of applications we're going to do with this this section. And once we have the equation of the function of the derivative, we can set that equation equal to 0, and everywhere the slope is 0, we know we have a horizontal tangent line, right? So horizontal lines look like this, right? And they have slopes of 0. If f prime of x is undefined at a specific value of x, then we know there's no tangent line at all. And if f prime of x equals a real number m that's non-zero, right, then the tangent line is parallel to a line of slope m where m is some number. So technically 1 and 3 are saying the same thing because 0 is in fact a number, but we usually pull the horizontal tangent lines as in their own separate category, and when we get a little bit further into this, you'll see why we do that, because it's telling us more information about our function. In an applied setting, right, the quantity f prime of a represents the rate of change. So we saw that in the difference quotient. We're looking at the change in y values over the change of x values. So one of the things we want to make sure we really understand what's happening in this section are the units. So if your original function y, right, is measured in miles, and the input variable x is measured in hours, well then your derivative is going to be miles per hour, because the change in the original y would be in miles, and then when we divide that by the change in our x variable, that's where we get the miles per hour. So what we end up saying is the function's original units, right, divided by the input variable's units. And a little bit later, when we start to take repeated derivatives, you'll see that we're dividing by this term every single time. If a function, right, is differentiable at a point, then it is automatically continuous at that point. However, a function may be continuous without being differentiable. So we actually investigated this in our last section when we looked at the absolute value of x. We saw that even though the function was continuous everywhere, you couldn't take the derivative at that sharp point, right? But in turn, if we know, right, that the derivative of a function exists, we can always assume that it is continuous, because you cannot take the derivative of something at a location where it is not continuous. So there are shortcuts to derivatives, but we are still not quite there yet. So make sure that if you have some prior calculus experience, that you don't attempt to use any of the shortcuts. We're sticking with the limit definition for this section.